right, guys. So picking back up with ice tables, there are some instances, like I said, the last example we did, you had to do the quadratic equation and put it in the calculator to solve for x. There is kind of a shortcut that you can use under certain circumstances. So let's look at this reaction. It says in air at 25 degrees Celsius in 1 atmosphere, the concentration of nitrogen gas is 0.033 molar. Oxygen gas is 0.00810 molar. And it says taking the nitrogen oxygen concentrations as initial values, find the equilibrium concentration of nitrogen monoxide that would exist in our atmosphere at 25 degrees Celsius. So looking at our reaction as given, we're going to set up our ice table. So we said nitrogen is 0.033 molar, oxygen is 0.00810 molar, and it did not say anything about us having nitrogen monoxide initially. So that is going to be set at 0. We have our K value, but that's all that we know. So we are going to have to figure out what our change is going to be and what our equilibrium concentrations are going to be. So this is where we have to use that factor of X as our change factor. Remember, nitrogen monoxide is 0. You cannot subtract from 0. So we have to add to our product side and subtract from our reactant side. Since nitrogen monoxide has a coefficient of 2, we are adding a factor of 2x. For nitrogen and oxygen, there's only one of them, so we are subtracting by a factor of x. So our equilibrium concentrations as we have it for nitrogen is 0.033 minus x. Oxygen is 0.00810 minus x. And nitrogen monoxide is going to be 2x. So whenever we plug this in, this would get really messy the way that it is, because we have two reactants with that negative x or minus x factor. Here's kind of the rule. If the K value is at least 100 times different than our concentrations, ignore x. So if your K value is at least 3 places different than your concentrations, you can ignore x whenever you are subtracting. So notice that our K value is 4.8 times 10 to the negative 31st. For nitrogen, 0.033 would be equivalent to 3.3 times 10 to the negative second. Negative second and negative 31st are 29 places different. So there we are going to be able to ignore x. If you look at the 0.00810, that would be 8.10 times 10 to the negative third. That is 28 places different than the 4.8 times 10 to the negative 31st. So here we can also ignore x. You cannot ignore x if that is the only thing there. So we still have to keep 2x because it's not being added or subtracted. So that is going to simplify our math when we are trying to solve for that x factor. And we're able to ignore x just because there's such a large difference in those magnitudes that our change there is going to be virtually negligible. So when we plug in for K, which is the 4.8 times 10 to the negative 31st, we have our product on top, which is going to be the 2x squared, divided by our reactant. So we can ignore those x's. So we have 0.033 and 0.00810. And yeah, again, make sure that you put those in parentheses. So we have to multiply by those to isolate X. So that is going to give us 1.28 times 10 to the negative 34th equal to, and I go ahead and simplify that side. So remember, this exponent is going to go to both the 2 and the x. So that's going to simplify to 4x squared. So if we're isolating x, we can divide by 4. Sorry, I don't have that number written down. So 1.28 to the negative 34th divided by 4 is 3.2 times 10 to the negative 34th. Or negative 35th, excuse me. That is equal to x squared. We are still trying to find x, not x squared. So you have to make sure to take the square root. And we get that x is equal to 5.7 times 10 to the negative 18th is our change amount. So when we go plug that back in, here's why we can ignore that x factor. If you do 0.033 minus 5.7 times 10 to the negative 18th, you still get 0.033. Because that x is so small, it's negligible. Same thing with the oxygen. It would end up being the 0.00810. But this specifically wants us to know the equilibrium concentration of nitrogen monoxide. Well, nitrogen monoxide is 2x. So if we do 2 times the 5.7 times 10 to the negative 18th, we get that that is 1.1 times 10 to the negative 17th molar. So it only wanted that one concentration, but being able to ignore X is going to help us out. So generally, if it's at least 3 decimal places different, ignore X, and that will save you some math, and it will be a little bit easier for you to solve for. All right, and let's look at this last problem. Here it says we have a reaction mixture initially contains a pressure of iodine that is 0.15 atmospheres, a pressure of chlorine that is 0.15 atmospheres, and a pressure of iodine chloride, excuse me, that is 0.1 atmospheres. Wants us to find the equilibrium partial pressures, the equilibrium pressures of all 3 substances. So this is giving us the reaction, and it's using Kp instead of Kc. It's the exact same thing that we've been doing, but remember Kp, whenever you write it out, uses parentheses instead of brackets. So we're setting this up the exact same way. We have our ice table. Oh, I went a little too far over. Tells us that iodine is initially 0.150. So if you don't have concentrations, you can plug in pressures, but make sure pressures are in the same unit. Chlorine has 0.15 atmospheres. The iodine chloride is 0.1 atmospheres. Now here is similar to a problem we did in the first video where we have initial amounts for everything. We don't know how much to change by, so we don't know which side to add or subtract from, so we have to find Q. So in finding Q, we have to take the pressure of our product, so the 0.100, squared divided by the pressure of our reactant, so 0.150 times 0.150. Remember, put those in their own parentheses whenever you're solving. So we get that our Q value is equal to 0.44. So we're comparing K and Q. K is greater than Q, so the reaction proceeds towards the products. So remember, that means that we are going to add on our product side, subtract on our reactant side by a factor of X. So this, remember, you have to use your coefficient. So iodine is going to decrease by X. Chlorine is going to decrease by X. The iodine chloride is going to increase by a factor of 2X. So when we are plugging that in to our equilibrium amounts, we have the 0.150 minus X for both reactants, and then 0.100 plus 2X for our product. So we have to plug this in. Notice that the K value is 81.9. Our coefficients for all of our reactants would be to like the negative first power. That is only like 2 places different. So we cannot ignore X here. However, the math does not have to be super complicated. I'm going to show you why. So we have our K value, the 81.9. That is equal to our product, the 0.100 plus 2X squared, divided by 0.15 minus X times 0.15 minus X. Because we have that twice, we can rewrite it as being squared, because it's the same thing being multiplied. So now that you have something on top being squared and something on the bottom being squared, we can take the square root of both sides and get rid of those squared factors. That will save us a little bit. So that will simplify to 9.05 equal to 0.100 plus 2X over 0.150 minus X. So we still have some math to do, but it's a lot simpler than we initially started out with, because we are not going to have a squared factor now. So we have to multiply by 0.150 minus X. So then we have 1.357 minus 9.05X is equal to 0.100 plus 2X. So we can get all of our X values to one side. Let me switch colors because there's a lot of red. So when we move our X's and our coefficients to one side or the other, we end up with 1.257 is equal to 11.05X. So when we divide, we get that X is equal to 0.114. So we can plug that back in to our equilibrium values. I'm going to change to green to show this. So if we do 0.150 minus 0.114, we get 0.036 molar for both of these. For the iodine chloride, 0.100 plus 2 times 0.114 gives us an equilibrium value of 0.328 molar. So you need all three values. Oh, excuse me. These are not molarity. These are atmospheres. That was my mistake. I got in the habit of doing molarity. So these are all atmospheres for pressure. Something that could come up is if it asked you for the total pressure. This goes back to unit 3 where we had Dalton's law of partial pressures. If we wanted to know what the total pressure of this is, remember the total pressure is equal to all the individual pressures added together. So we could do 0.036 plus 0.036 plus 0.328. That is another kind of secondary question that could come up from these. Ice tables are not easy. I know this, and it's a process. Every ice table might be slightly different based off of the information given. This is one of those things that you have to practice. So I would suggest going through and doing some of the textbook problems. Remember, my textbook keys are posted. And in the additional practice that's posted at the top of our unit calendar, in that equilibrium number 1 and equilibrium number 2, there are practice problems for finding equilibrium constant, reaction quotient, and using ice tables. I do not have anything additional planned for tomorrow other than practicing and preparing for your quiz. So utilize your time wisely to do some of the practice problems and go through and make sure you are comfortable solving for these.